When you implement vector search, especially for edge or on-prem deployments, you're effectively balancing three competing forces: speed, accuracy, and compute. One of the most important choices that's going to affect that balance is the embedding model you choose and how you configure it. So that's why in this video, you'll learn how embedding models work and how to evaluate them, so you understand the trade-offs to make between retrieval quality and search efficiency. Now, if you didn't catch the first video in this series, where we covered vector databases and similarity search at a high level, here's a quick recap. Vector databases came about because traditional text-based search can only match on exact keywords, not similarity or relevance. By using an embedding model, input data such as text, images, or audio is encoded into a vector embedding, a list of numbers that together capture semantic meaning, where similar concepts are positioned closer together in vector space. A vector database stores these embeddings and enables similarity search by encoding a query into an embedding, then comparing it against stored embeddings to retrieve the closest matches. Now, closeness is a useful conceptual model, but to understand how an embedding model actually encodes similarity, we need to be a bit more precise. Let's illustrate this with a diagram. For simplicity, this is a two-dimensional plane, but in reality, embedding spaces often have hundreds or even thousands of dimensions. You can think of each vector as an arrow pointing outward from a central origin, where the direction represents semantic meaning. Similarity, then, is just a measure of how closely the direction of two vectors align. Vector alignment works well for semantic search, as vector magnitude tends to be irrelevant. Similarity is typically calculated using cosine similarity or dot product. But for feature-based similarity search, where vectors could represent measurable values, such as image colors or sensor readings, similarity can be measured as the distance between 2 points in vector space using Euclidean distance, also known as L2. So now that we've covered how embeddings make similarity search possible, let's dive into embedding model fundamentals. Embedding models are different from LLMs, as they have just one job: to encode input into an embedding. They don't generate content. Embedding models are trained using techniques like contrastive learning, where the model is shown pairs of related and unrelated examples and learns to pull similar items closer together while pushing dissimilar ones further apart. While every embedding model performs essentially the same task, they can vary significantly in their capabilities, infrastructure requirements, and the embeddings that they produce. So we can break embedding models down into 7 typical characteristics. Modalities are the types of input data the model can encode, such as text, images, audio, or even combinations of multiple data types. Capabilities represent the functional strengths of the model. For example, English only versus multilingual support. Parameter size is the model's parameter count. Larger models can capture more nuanced semantic relationships and encode meaning more precisely, but require more compute and memory to run. Dimensions is the length of the output embedding. Higher dimensions capture more detail, but require more storage and compute. Context window is the maximum number of tokens the model can accept when generating a single embedding. Training data is whether the model was trained on general data or domain-specific text, like biomedical or legal, which affects how well it handles specialized vocabulary and nuanced concepts. Deployment mode is whether the model runs locally in your infrastructure or is accessed remotely via API, typically driven by data locality and latency requirements. And finally, open versus closed weights refers to whether a model's learned parameters are publicly available, which determines if you can fine-tune or retrain it. So those are the key characteristics to evaluate when choosing an embedding model. Now, some of these are pretty self-explanatory, so let's now look at the 3 that directly impact storage and performance: parameter size, dimensions, and context window. Parameter size reflects the model's capacity to capture nuanced semantic relationships. Each parameter is a learned weight adjusted during training, so models with more parameters can capture more subtle relationships between words and concepts when generating embeddings. However, that added capacity comes at a cost, as larger models require more memory and compute to run. If model size becomes a constraint, you can either choose a smaller model or run a quantized version of a larger one. Now, which approach is right for you depends on several factors, and we'll cover all of this and more in a quantization video coming up later in the series. Now, let's take a look at dimensions. While parameter count determines how semantically nuanced the model can be, dimensions, which are the number of values in an embedding, determine the level of semantic detail that's captured. Here's a simple way to think about it. Imagine describing coffee using dimensions. The first could be milk or no milk. The second, caffeinated or decaf. The third could be the extraction method, espresso, pour over, or French press. And fourth could be the roast level, light, medium, or dark. Each dimension is capturing a different aspect of meaning. More dimensions allow for greater specificity, but they also create larger embeddings, increasing memory, storage, and compute costs at query time. And more dimensions don't automatically improve retrieval quality. The right dimension size is simply whatever you've evaluated to be performing well for your data and queries. Most embedding models have a fixed output dimension, but some models, such as Google's Embedding Gemma, use advanced training techniques that allow a lower dimension value to be chosen without significantly compromising semantic quality. Now, while there's no universal best dimension size, historically, different ranges tend to suit different scales and use cases. 128 to 256 dimensions is ideal for real-time applications, mobile devices, and edge deployments, where speed and memory efficiency are the limiting factors, often sufficient for FAQs and short documents. 384 dimensions is a common middle ground that balances semantic richness and storage cost, and is ideal for many general-purpose RAG applications. 512 to 768 dimensions provides more nuanced semantic representation and is often used for larger knowledge bases or more complex domains where subtle distinctions matter. And 1024 plus dimensions is typically used in high-scale or high-fidelity systems where maximum representational capacity is desired. One final thing to remember is that the dimension value at search time must match the dimension value at ingestion time. Moving on to context window, this defines the maximum number of tokens a model can process when generating a single embedding. For most vector search use cases, a 512 token window, which is roughly 300 to 400 words, is usually sufficient, since content is typically chunked into paragraphs or pages or logical segments. Larger context windows only really become necessary when an entire document needs to be encoded as a single embedding. This is when similarity search is operating at the document level, not the text chunks within them. Content chunking is a deep topic in itself, and the strategy you choose can significantly impact retrieval quality. So we'll be dedicating a full video to it later in this series. So now you understand what embedding models are, how they encode semantic meaning, and how to weigh up the various factors which affect retrieval quality and search efficiency. Thanks for watching, and I'll see you in the next video.